An RF amplifier is a two-port active device that boosts the input power. For example, if this is the port 1 of the device and this is the port 2 of the device, if there is P in coming in, the total power that is coming in is P in, then the output power P out is going to be greater than P in, and essentially the amplifier is going to boost the input power. It is symbolically represented by this triangular shape here, and in a communication system where there is a certain transmitter and a certain receiver, there are amplifiers both in the transmitter and the receivers. The transmitter receiver, which essentially sends out a very high output power, is called as a power amplifier, in short PA. And in a receiver, the signals that you're going to receive is very weak, typically is going to be very low, essentially because it has passed through that wireless medium picked up by the receiver antenna, and the amplifier that you have first to boost that signal to be able to further demodulate and decode the information out is called as a low noise amplifier. It's called as a low noise amplifier. Both of these are represented by a triangular shape like this. So in some sense, the gain of the amplifier is essentially the output power over the input power. In a typical communication system, let's say some kind of a Bluetooth link, there could be a certain transmitter that has a certain transmitted power, and there could be a receiver which is receiving at a certain distance. So depending on the distance of the receiver, the signal received can be very low in value. For example, in the Bluetooth protocol, it is necessary that the receiver has a sensitivity of minus 60 dBm. That means it should be able to receive any Bluetooth signal which is all the way minus 60 dBm, and the transmitted power is typically 0 dBm. And 0 dBm transmit power, if you were to convert that to linear scale, is going to be around 1 milliwatts. We know that 0 dBm is 1 milliwatt, and minus 60 dBm is like 1 nanowatt, or which is 1 into 10 to the power minus 9 watts. So which is very low power. And further away the transmitter is from, further away the receiver is from the transmitter, or the transmitter is further away from the receiver, the signal received is going to be lower than minus 60 dBm, and it is not necessary that the Bluetooth link between the transmitter and receiver could be established then. Now in a receiver, what you end up getting is going to be a minus 60 dBm signal, but to be able to decode it and to be able to demodulate it further, we would want to boost it using a low noise amplifier whose gain is maybe 60 dB. Then you would end up getting an output power of 0 dBm. So then the amplifier is said to have a gain of 60 dB. In other words, the P in for the amplifier is minus 60 dB and the P out is 0 dBm. So this gain being the ratio of the output over the input, it's typically in dB. The output in dBm is going to be P input to the transistor in dBm plus the gain of the transistor in dB. So it's very important that the output and the input are in the same units. If it is in milliwatts, or in this case dBm, then the input should also be in dBm. If it is dB micro, then this is dB micro as well. Whereas gain being the ratio of two quantities is going to be always dimensionless and is going to be in dB. So let's see further in detail how this gain is going to be, whether and some parameters of how this gain is going to look like, gain of an amplifier is going to look like. So typically if you have a certain input voltage to the amplifier, there is going to be an output where in an ideal case, this is an ideal case where the output is proportional to the input by a factor of beta, and beta is said to be the linear gain. So if the input is 1 volt for example, and beta is 10, then the output is 10 volts. Let's say for 1 volt you get an output of 10 volts. If you have maybe 5 volts, then the output is 50 volts, so on and so forth. So then the beta is a factor of 10. So this can be more pictorially represented this way, where the input is this blue curve. So this is going to be the input signal and this is going to be the output signal. You see that in this case, for example, the input signal is having a V peak to peak of 2 volts in total, that is with plus and minus 1, whereas the output is having a total swing of 4 volts peak to peak. And you see that the gain beta in this case is going to be 2. But if you notice, this is in the time domain. The same thing can be observed in the frequency domain, where the spectrum of this time domain pulse is seen, and you see that this is at 2 gigahertz. The input having 1 volt is being boosted to a voltage of 2, the amplitude of magnitude 2. So it is said, means that the time domain gain can also be correspondingly defined in frequency, and we can see that the output voltage in frequency, the V out, which is a function of frequency, is going to be the gain times the input signal. So G is going to be the gain of the amplifier, and that can also be a function of frequency. For example, here the gain is 2 at 2 gigahertz. It need not necessarily be same at a certain different frequency. Let's say you had a signal at 6 gigahertz. Maybe the output at 6 gigahertz might be lower than the input, maybe, meaning that the gain that you had at 2 gigahertz is not the same as what gain that you have at 6 gigahertz. In that sense, the gain of the amplifier is a function of frequency. So if you go ahead and plot the gain versus frequency, we see that there can be different responses possible, but one thing that is nice to property that amplifiers have is that the gain bandwidth product is a constant, meaning if you have a certain amplifier with a certain gain, and if you go ahead and define a minus 3 dB bandwidth, which means from the peak gain, if I go to a point which is minus 3 dB, and if I were to draw the bandwidth, extract the bandwidth out of it, the frequency bandwidth, for which the gain is more than this value. So for the red curve, it's going to look like that. And for the blue curve that we see here, we can see that the blue curve, we see that the gain is a lower value than the red curve. And if you see the minus 3 dB point, we clearly see that the 3 dB bandwidth is much wider than that of the red curve, meaning that by compromising the gain, the bandwidth has improved. In other words, the gain, if gain goes up, the bandwidth goes down, maintaining the gain bandwidth to be a constant.